Let's take a look at a couple of additional examples of integrals that we're going to calculate using trigonometric substitution. Starting with the integral of 1 over x squared multiplied by the square root of 16x squared minus 9. Now what we have seen is that we can use trig substitution to replace a sum or difference of squares by a single square, and this is practical in particular when we want to get rid of a radical. So here we have under a radical a difference of squares, but what we want to have to use trig substitution is one of the square being just the square of the variable. Here we have 16x squared instead of simply x squared. So the first thing we're going to do is make it just the square of the variable, and there's a couple of ways we could do that. We could write 16x squared as 4x squared and use the substitution with u equal 4x, or we can simply factor out 16, and I'm going to go that way. So if I factor out 16 under the square root, I get 16 multiplied by x squared minus 9/16, and then when we pull out the 16 out of the root, we get a 4 at the bottom, and I'm going to pull that out of the integral as a constant in front of the integral, which is simply 1/4. So now we are in a standard situation to use trig substitution. Just to remind you what we have seen about the type of substitution and that we use in each situation. This is a table of trig substitution that we have seen in the previous video, and you see that we are in this kind of situation. We have the square root of x squared minus a squared, and in that case we're going to use x equal a secant of theta as our trig substitution, restricting yourself, well, for instance, to theta between 0 and pi over 2, or to theta between pi over 2 and pi. So we're going to, in this case, pick the interval theta between 0 and pi over 2, which corresponds to asking x to be greater or equal to 3/4, because that means x over a is greater than 1, and here a is 3/4. Because our a squared is 9/16, that means a is 3/4, and so we take for x 3/4 of secant theta. So if we pick that substitution for x, and dx is 3/4 of the derivative of secant. Secant is 1 over cosine, so that's cosine to the negative 1. When we differentiate, we get negative cosine to the negative 2 multiplied by the derivative of cosine, which is negative sine. The two negatives cancel out, and we get sine theta cosine theta to the negative 2. In other words, we have 3/4 sine theta over cosine square theta d theta. We're going to replace dx by this quantity and x squared by 9/16 of secant squared. So this is what we obtained that way. So we have this 1/4 in front that is multiplied by the 3/4 from the dx, and then at the bottom x squared is multiplied by 9/16 of secant squared, and similarly under the square root. That means that under the square root we can factor out 9/16, and we're left with secant squared theta minus 1 under the root. So this 1/4 times 3/4, that's 3/16, and then we have this 9/16 at the bottom. We can pull it out, and so it's the reciprocal of 9/16, in other words 16 over 9. So I have 3 over 16 multiplied by 16 over 9. The 16 cancel out. I'm left with 3 over 9, which is 1/3. Then here I have sine theta over cosine square, and the secant square at the bottom. Secant square at the bottom means cosine square at the top, because secant is simply the reciprocal of cosine. So I get cosine square at the top. I get cosine square multiplied by sine divided by cosine square. The cosine square cancel out, and I'm left with simply sine theta at the top, and at the bottom what is left is now simply the square root. I can pull out the 9/16 out of the square root, and the secant square theta minus 1, this is where we use the trig identity and this is how we pick the trig substitution. This is simply tangent squared. So when I pull out 9/16 out of the root, I get 3/4, and then I'm left with root of tangent square theta. So 1/3 multiplied by the reciprocal of 3/4, that's 4/9. And because theta is between 0 and pi over 2, that means that the square root of tangent squared, which is formally just absolute value of tangent theta, is actually tangent theta because we picked the interval for x corresponding to theta between 0 and pi over 2. In other words, the tangent is positive on that interval. So we replace square root of tangent squared by tangent, and as I said, 1/3 multiplied by the reciprocal of 3/4 is 4/9. And now sine theta over tangent theta, tangent is sine over cosine, so we are left with simply 1 over 1 over cosine, in other words, simply 4/9 of the integral of cosine. Antiderivative of cosine is of course sine theta, and therefore our integral is 4/9 of sine theta up to a constant. So now we're going to use that x is 3/4 of secant theta to try to rewrite this expression as a function of x rather than a function of theta. And to do that, you see that if x is 3/4 of secant theta, that means secant is 4x over 3, and that is the ratio of the hypotenuse to the adjacent side. So we can represent this in this triangle where we have an hypotenuse of length 4x and an adjacent side adjacent to the angle theta of length 3. The remaining side, using the Pythagorean theorem in this right triangle, is square root of 16x squared minus 9. So now we want to rewrite 4/9 of sine of theta in terms of x, and you see that in this triangle sine theta is the opposite side over the hypotenuse, in other words, square root of 16x squared minus 9 over 4x. When I multiply that by 4/9, you see that the 4 cancels out, and we're left with square root of 16x squared minus 9 divided by 9x up to a constant. And this is valid for x greater or equal to 3/4 because this is what we picked for the interval for the trig substitution. Now one more example, that the kind of example that we will see again when we talk about integration with partial fractions. You will see that a function like that is what we will call a partial fraction. So we want to integrate 1 over x squared plus 4 squared. If we had just integral of 1 over x squared plus 4, we would know what to do. This would be an arctangent, but we have this square. So now we can try to use the same approach. We don't have a radical that we want to get rid of, but we still have a power of a sum of squares. So if we write that as a single square, I will have a power of a single square, in other words, just a single power, and that might be easier to handle. So let's try to see what we get using this approach. We have a sum of squares, and therefore that means that we're going to use x equal a tangent theta for our trig substitution. In our case, a is 2, because a squared is 4, so we're going to use x equal 2 tangent theta, restricting theta to the interval negative pi over 2, pi over 2, excluding the endpoints. So in that case, dx is 2 times derivative of tangent, which is secant squared of theta d theta. So we replace dx by this quantity and x squared by 4 tangent square theta. So this is what we obtain. So we can pull out the 2 at the top. Inside the square, we can factor out the 4. So we get 4 times tangent square theta plus 1. And if I pull out the 4 out of the square, it gives me a 16. Therefore, I'm left with 2/16 as a multiplicative constant in front of the integral. Secant square theta at the top, square of tangent square plus 1 at the bottom. Now we use the identity 1 plus tangent square is secant squared. So what I have at the bottom is actually secant squared squared, in other words, secant to the 4th. I have secant squared at the top, secant to the fourth at the bottom. I'm left with 1 over secant squared. And 1 over secant squared is really just cosine squared because secant is a reciprocal of cosine. 2 over 16, of course, simplifies as 1/8 as a multiplicative constant in front. So we're left with 1/8 of the integral of cosine squared theta d theta. It's the integral of an even power of a trig function, and we've discussed that before. It's a standard situation where we use a double angle formula. We can replace cosine squared theta by cosine 2 theta plus 1 over 2. Pulling out the 1/2, we get 1/16 of the integral of cosine 2 theta plus 1. An antiderivative of cosine 2 theta is 1/2 sine 2 theta. When I multiply by 1/16, I get 1 over 32 sine 2 theta. And then an antiderivative of 1/16 is simply theta over 16. Now we want to rewrite this in terms of x rather than theta. And to do that, we're going to use, again, the double angle formula, but for the sine. Sine 2 theta is 2 sine of theta cosine of theta. And I'm going to use that to write everything back in terms of theta because that will be easier for us to get back to x. So what we have is 1 over 32 times 2 sine theta cosine theta. 2 over 32 is 1/16, so we can factor out 1/16, and we have sine theta cosine theta plus theta. And now we want to write that in terms of x. And because x is 2 tangent theta, that means tangent is x over 2, and that's because we have restricted theta to negative pi over 2 pi over 2, that means theta is arctangent of x over 2. And on the other hand, if tangent is x over 2, and we write that in a right triangle, x over 2 is a ratio in this case of the opposite side to the adjacent side. And the remaining side, using the Pythagorean theorem, is of course square root of x squared plus 4. So now we are in a position to replace everything in terms of x, because now sine of theta is the opposite side over the hypotenuse, in other words x over root of x squared plus 4. Cosine is the adjacent side of our hypotenuse, 2 over root of x squared plus 4. So when we multiply them together, we get 2x over the square root squared, in other words 2x over x squared plus 4. So we replace sine theta cosine theta by 2x over x squared plus 4 and theta by arctangent x over 2, and we obtain a function of x, and that gives us an antiderivative as a function of x. Now it's time for you to do some homework.